Thanks for the opportunity to give an oral presentation. Today, I'm going to talk about our work NeurEPDiff, neural operators to predict geodesics in deformation spaces. So, let's start with deformable image registration, and I will share with you some motivations. Deformable image registration has a vast range of practical applications, like shape analysis for marine life study or for medical image domain, Alzheimer's disease diagnosis. This is a visualization of registration from source image to the target image. The third column shows the deformed images, which are very similar to the target images. The fourth column displays the results of deformation fields phi, represented by the determinant of Jacobian of phi, which provide informed information to analyze shape changes. Specifically, the red region shows expansion, the light blue shows no volume changes, and the dark blue shows shrinkage. In the specific case of registration from a healthy subject to the Alzheimer's disease, the red region shows the ventricle shape expanding, and the blue region shows the gray matter is shrinking, which are indicative of brain tissue loss, so the patient suffers from memory loss. Actually, ventricle shape is very important biomarker to identify whether a patient is healthy or not. While many registration algorithms can provide us with the final deformation fields, seldom reveals how the deformations occur gradually, which is also very critical in shape analysis. For example, the animations are showing the gradual deformation process generated by two types of registration algorithms. They are time-dependent velocity fields with geodesic shooting and the stationary velocity fields. This shows that geodesic shooting effectively captures the gradual deformation process, while in the SVF, there are seldom deformations in the first steps. All deformations suddenly happen in the last few steps, failing to capture the deformation process. Unfortunately, conventional methods suffer from expensive computational costs when performing geodesic shooting in high-dimensional image space. Moreover, currently low deep learning registration networks have been developed to learn the deformation process. So, to overcome these challenges, we proposed NeurEPDiff, the first deep learning network to learn the geodesics in deformation space and to understand the gradual deformation process with greater efficiency. Next, I will quickly touch how to perform diffeomorphic image registration with geodesic shooting to establish the theoretical foundation of our method. So, diffeomorphism is bijective, smooth, and invertible transformation, which is ideal to maintain an intact topology of objects presented in images. The problem to find the optimal solution diffeomorphism phi is typically formulated as the minimization of the allergy function, which includes two items. The first is the image matching term that measures the distance between the deformed source image and target image. Common distance functions include mean square error, mutual information, and cross-correlation, and plus a regularization term to guarantee the smoothness. Well, how to find the best diffeomorphism? Suppose we have a manifold where each point on it corresponds to a diffeomorphism. Here E is the identity transformation and phi is any diffeomorphism. We have many paths to connect E to phi. Well, LDDM algorithm proves the optimal solution to be a geodesic, also known as the straight line on the manifold, which is uniquely determined by the initial velocity under the constraint of geodesic shooting equation, which we call EPDiff equation. To be more specific, given any initial velocity, the EPDiff equation enables the generation of a time-dependent velocity fields along the geodesic flow, which can be used to integrate the second equation to obtain the entire geodesic flow of diffeomorphisms, which in turn allows us to understand the gradual deformation process. You don't need to worry about the mathematical symbols in the equation, except the key operator, which is an inverse operator of the Laplacian operator to employ a smoothness on the transformation field. Because it's a low-pass filter under the Fourier transformation, suppressing high frequencies in velocity fields. So, Flash algorithm propose a faster version of EPDiff equation to truncate the high-frequency modes and perform geodesic shooting in the no-dimensional band-limited Fourier space. So we have the new version of the geodesic shooting equation, named Fourier EPDiff. So as you know, the recent NeurEPDiff has been very popular to be used as a surrogate model for the numerical solutions of partial or ordinary differential equations. They are carefully designed neural networks to learn the solution functions that map any initial conditions of the family of partial or ordinary differential equations to the output solutions, which are more computational efficient than traditional numerical methods. So, in our case, we want to design a neural network to learn the solution function of the specific partial differential equation, Fourier EPDiff. The motivation behind this is to give the neural network the ability to understand the entire physiological process of how the object changes from one image to another, and in the meanwhile to enhance the computational efficiency when computing the geodesic flow. The work deserves our attention as it provides us with a new approach to performing shape analysis. So let's take a look at how we design the architecture of NeurEPDiff to learn the solution functions. As you see in the figure, the key component is the network G theta. Theta is the network parameters. We adopt an iterative architecture with tau steps of circulations of G theta to learn the entire solution function of Fourier EPDiff. In each iteration, we only learn one submapping from V0 tilde to V1 tilde, from V1 tilde to V2 tilde, and so on up until the endpoint V tau tilde. Once the G theta is well learned, it can be used as a surrogate model to compute the solution of the geodesic flow from the origin to the target, given any initial velocity. Next, I will present the detailed design of the network G theta. So, how to design G theta to learn the highly complex and nonlinear mapping function for Fourier EPDiff? Firstly, we use a kind of encoder P tilde to lift the input signals to a higher dimensional channel space, or you can say it the latent space. We let the higher dimensional signals to go through the iterative evolution layer. After that, we project the representation back to the original space with a decoder Q tilde. As to the iterative evolution layer, we design an alternative combination of linear operators and nonlinear activation functions to enhance its nonlinear expressiveness. Specifically, we alternatively use W tilde and H tilde with a complex-valued activation function, sigma. W tilde are global convolution colors, H tilde are local linear transformations. Our activation function, sigma, will apply real value to G loop, separately on both the real and the imaginary part of a neuron to simulate a complex valued activation function. Jilu is a continuous but nonlinear activation function, which is similar to ReLU. What's more, we impose a smoothing operator K in our activation function, which is an inverse operator or Laplacian operator mentioned above, to enhance the smoothness of the output signals. Actually, the design is inspired by the recent design of Fourier neural operator. The main difference is that our NeurEPDiff deals with band-limited complex value signals, while the previous work deals with four-dimensional real value signals. So next, I will move on to how to perform diffeomorphic image registration with NeurEPDiff. As a prerequisite, we should first train NeurEPDiff offline under the supervision of numerical solutions of Fourier EPDiff. E theta is the loss function, n is the number of training data. V tilde n is from the numerical solutions of Fourier EPDiff. G theta represents a solution from our NeurEPDiff. And the IEG recognizes the network parameters theta. Once the NeurEPDiff is well learned, it can be used as a surrogate model to fast predict the geodesic on various resolution of images when we do image registration. This slide represents how to perform diffeomorphic image registration with the NeurEPDiff. What we do is, in every iteration of optimizing the registration analogy function, we replace the numerical computation of geodesic shooting with our NeurEPDiff. We use NeurEPDiff to do forward shooting, given any initial velocity, to connect the source image to the target image. We have the analogy function in the conventional way, including an image matching term and a regularization term to guarantee the smoothness of the deformation. Generally speaking, we are also going to solve optimization-based problem. We use the analogy function as error correction item to compute the gradient related to the initial velocity, and then update it through gradient descent. We iteratively optimize the initial velocity until the analogy function converges to a stable point. So, this is the main idea to perform diffeomorphic image registration with NeurEPDiff. Next, I will move on to the experimental results. But before I move on to it, I want to talk a little bit about why NeurEPDiff is resolution-invariant. Firstly, NeurEPDiff is designed to learn the mapping functions. As long as it is well learned, it should be applicable to image of various grids, as it has captured the functions behind. And the previous work, Fourier neural operator for parametric partial differential equations, also provides some mathematical testification. Here, I would like to give some more empirical explanations. So let's review the architecture of NeurEPDiff. Firstly, the global convolution kernel H tilde deals with fixed frequency modes, as we truncate high frequencies, while the value approximates to 0. So the truncated information is actually less important. Secondly, it's also partly because the encoder and the decoder design of P tilde and Q tilde. When we use P tilde to lift input into higher dimensional channel space, even if we truncate the higher frequency modes on each dimension, we may also recover them from certain lifted channels. So finally, let's move on to the experimental results. Firstly, let's take a look at the registration performance on 2D synthetic bull's eyes. We train 2D NeurEPDiff with 2,000 volumes of training data with a size of 64 squared. Then we test the model on different levels of higher resolutions. This slide shows the registration results on images with the size of 192 squared. We can find that even though our model is trained on a low image resolution, the predicted results are fairly close to the estimates from registration algorithms of both Flash and LDDM on higher resolution. We also do experiments on 3D real brain MRIs from OASIS. We train 3D NeurEPDiff on lower resolution of 64 cube with 2,000 volumes of training data. Then we test the model on various higher resolutions. This slide displays an example of the comparison between the manually labeled segmentations and the propagated segmentations on 3D brain MRIs at the resolution of 192 cube generated by wall methods. It clearly shows that our method generates very similar segmentations to both Flash and LDDM, aligning fairly well with the manual delineations. This slide gives some more quantitative analysis of the results. In the top panel, we compare the runtime of solving EPDiff equation on different scales of resolutions on a CPU machine. It shows that our NeurEPDiff gains orders of magnitude speedup compared to other baselines, while maintaining a comparable registration accuracy evaluated through the average dice on the bottom panel. Here, we extend the dice evaluation to 4 brain structures, using 100 registration pairs at different scales of image resolutions. The red line represents our method's results, which clearly show that our method achieves comparable results to wall baseline models. Finally, we compare the convergence graphs of total registration errors by wall methods on different levels of resolutions. The red line represents our method, NeurEPDiff. It shows that our method consistently converges to a better solution than LDDMM at multi-different resolutions and a slightly worse but fairly close solution to Flash. So, let's come to the final part. Generally speaking, NeurEPDiff is the first neural paper to fast predict geodesics or diffeomorphisms in a low-dimensional band-limited space. The performance of NeurEPDiff is invariant to image resolutions, which can be generalized to various resolutions of image grids. Our future work will focus on further statistical shape analysis with our proposed network architectures NeurEPDiff. Our future work will also be dedicated to refining network architectures, making them more efficient and advanced to learn the mappings in partial differential equations. And another interesting work of ours has been submitted for review, which incorporates the proposed NeurEPDiff into the unsupervised learning process of image registration. This approach endows the networks with the ability to understand the entire physiological mechanism of deformation process from one object to another, rather than solely pursue image matching. So that's all about our work NeurEPDiff. And we have uploaded the code to GitHub. Welcome to download it and looking forward to receiving your valuable feedback. Thank you.